All right, hi, this is Module 11, which is ocean currents. So basically, when we look at ocean currents are what drives our weather and basically our climate on Earth. So without the oceans, our climate would be much different. So if we look at this is a picture of the different currents. So we talked a little bit about the Coriolis effect last time. So the Coriolis effect is causing ocean currents in the northern hemisphere, which is above the equator, which would be right here on this line. So every current in the northern hemisphere, notice how it moves clockwise. So clockwise here, and then down in the southern hemisphere, they're counterclockwise. So counterclockwise here. And this is because the Earth is spinning this direction. So the Earth is spinning counterclockwise if you look from the North Pole. So that causes the winds to be deflected as the Earth is moving, and then you've got hot air near the equator, colder air near the poles, and so that's a huge convection current as well. And then we also talked about the Hadley, Ferrel, and polar cells. So all of these things work together. But if we look at the currents are driven kind of similar to air. So the ocean is not attached directly to the Earth. So as the Earth spins, the oceans want to move as well, and they move because of air as well. So the air currents are moving that direction. The currents in the ocean are moving that direction as well. And the currents are really important. The ocean is really important for distributing heat. So we've got this unequal heating on the Earth's surface. Well, at the equator, you get more intense radiation, and at the poles, you get less. So this is what helps to kind of equalize that unequal heating. So the heat along the equator, so you can picture this water as warmer. So this warm water is circulating and bringing warmer water up into the northern Pacific here. And then you can see this California current is colder water coming down. That's one of the reasons why our water on the coast is so cold, because it comes from the north. So it's not coming from the equator, so it's colder water. And then down here, same thing. So as the current moves around, it is bringing this colder water next to South America. And then if you notice on the west coast of all continents, so west coast of Africa, west coast of South America, west coast of North America, the currents are cold. So there's always colder water on the west coast. And then if you look on the east coast of these continents, so the east coast of North America, east coast of South America, east coast of Africa, it's warmer currents. So if you ever been to like the Atlantic over on the east coast, New York is about the same level as Washington, so or Oregon, but you can get in the water there, and it's really warm. Versus up here in Northern California and Oregon, the water is extremely cold. You need a wetsuit to get into it, and that's because the currents are bringing that heat. So they are redistributing the heat around the Earth. So extremely important. All right, so this is going to show that current. There's no sound on this video, but it's going to show the currents. So it's just kind of neat to watch. So I'll play that. And so as we get closer to England is very warm because these currents are coming up. The Gulf Stream is coming up and bringing and redistributing this warm air. And then notice how the air, or not the air, but the ocean is diving. So these currents right here are diving down. And this whole distribution is called the thermohaline conveyor belt. And so that colder water sinks and it moves along the bottom of the ocean, and it's going back to the equator, and as it warms it rises, and that whole circulation pattern continues. And so this is due to temperature. It's also due to salinity, so salt of the water. So that's why it's called the thermohaline conveyor belt. So thermo is heat, haline is salt, and it's a big conveyor belt that distributes heat around the world, around the globe. It's extremely important, like I said, for keeping climate at bay and just redistributing that heat everywhere. All right, so if we look at the next term here, upwelling. Upwelling is the upward movement of ocean water. So in California, we have a lot of upwelling, and this has to do with longshore currents. So the longshore currents are coming down, the California current coming down along California, and then it's displaced, so it's replaced by water coming up from the bottom, and that water, that cold water, can hold more nutrients. So the colder the water is, the more oxygen, the more nutrients it can hold. And so that comes up. It's also colder, but it comes up and it creates this nutrient-rich water, which is really important for fish populations. So on the West Coast, where we have the colder currents, that is, there's upwelling occurring because there's longshore currents. And so that upwelling is bringing this nutrient-dense water. So we have a lot of life off of the West Coast of continents. More so than we do off the east coast of continents. And that's just because of this upwelling. So it's very, very, very important for nutrients and for organisms and life off of the west coast of continents. So upwelling is very important. It will come up again, especially when we talk about fisheries. All right, so here's that thermal haline circulation. I can move my picture off to the side, put it up here. So you can see here, this is that same circulation that we saw in that video. So this colder water, which happens to be more dense because of temperature, but it's also more dense because of salinity as well. So it's moving all along, and you can see it circulates throughout all the oceans. All the oceans are connected, even though they're named different, they're connected. And so they circulate around the entire globe. And this can take hundreds of years, but the water circulates throughout the entire globe. And so that is thermo refers to heat. Because you've got unequal heating. But when you have unequal heating, you also have evaporation, you have condensation, precipitation that creates different salinities on Earth as well. And so that haline refers to the salt circulation. Oops, I skipped one. So in this video, it's going to talk a little bit about that circulation.
The ocean conveyor belt and the Gulf Stream. Ocean currents have a direct influence on our lives. They determine our weather, our climate, and much more. The ocean currents and wind systems transport heat from the equator to the poles and operate like a large engine for the global climate. In the oceans, there are numerous currents. The so-called ocean conveyor belt is very important for our climate. This term describes a combination of currents that result in 4 of the 5 global oceans exchanging water with each other. They form a worldwide circulation system. The conveyor belt is also called the thermohaline circulation, with thermo referring to the temperature and haline to the salt content of the water. Both determine the density of the water. While the masses of water may be moved in part by wind, primarily the different densities of the global oceans are responsible for their movement. Warm water has a lower density and rises, while cold water sinks. The water's density also increases with a higher salt content. At the equator, the heat from the sun is especially strong, resulting in a lot of evaporation and thus a rise in the water's salt content. That is where the Gulf Stream begins. The Gulf Stream is very important for the European climate. Its length of 10,000 kilometers makes it one of the largest and fastest ocean currents on Earth, and it's very warm. At roughly 2 meters a second, it brings up to 100 million cubic meters of water per second towards Europe. A constantly blowing wind, the southeast trade wind, drives warm surface water to the northwest into the Gulf of Mexico, where it heats up to 30 degrees Celsius. The turning of the Earth and the west winds then direct the Gulf Stream towards Europe and split it up. One part flows south, another east to the Canary Current, and a third part flows north, where it releases a lot of heat into the atmosphere as the North Atlantic Current. The water becomes colder there. Its salt content and density rise on account of evaporation, and it drops down between Greenland, Norway, and Iceland. There we also find the largest waterfall on Earth, the so-called chimneys, roughly 15-kilometer wide pillars with water falling up to 4,000 meters. 17 million cubic meters of water per second, or roughly 15 times more water than is carried by all the rivers in the world. This creates a strong maelstrom which constantly pulls in new water and is the reason that the Gulf Stream moves towards Europe. Countless species use the Gulf Stream as a means of transport on their trips from the Caribbean to northern areas. But it doesn't just bring us animals. An enormous quantity of warm air also comes with it. In order to produce the same heat which it brings to the shores of Europe, we would need 1 million nuclear power plants. That's why we also call the Gulf Stream a heat pump. Without it, the temperature would be significantly colder here, at least 5 to 10 degrees. Instead of lush fields, we would have long winters and sparse ice-covered landscapes in Europe. In the last few years, scientists and pundits in the media have repeatedly expressed the fear that the Gulf Stream could come to a standstill due to climate change. Because if the polar caps actually melt, the salt content in the water off Greenland would fall, as would its density. The North Atlantic current would no longer be heavy enough, and so it wouldn't sink as usual. In the worst case, that would bring the Gulf Stream, our heat pump, to a stop. Some climate experts also assume that climate change could compensate for this effect. We know that it can be normal for the climate to change by looking at the development of the Earth over the last few million years. There are ice ages and warm periods. In the last ice age, a gigantic flood of melting water crippled the heat-bringing North Atlantic current, covering the northern hemisphere in ice. Scientists have different views on the impact that climate change will have on the global ocean conveyor belt. But one thing is clear: when the climate changes, then the complex system of ocean currents and winds, which has remained fairly stable since the last ice age, will change in ways that we don't yet understand.
All right, so that was a lot of information there. But we have the last thing to talk about. We just have El Nino. So El Nino is something that occurs every 3 to 7 years. And so what happens here is this is normal year. So normal year, we have these deep upwellings occurring here. So this is South America. And then we've got the trade winds. So the trade winds flow this direction in the southern hemisphere. In the northern hemisphere, they're flowing like this. So kind of opposite. And so they converge here at the equator, which also happens to be the ITCZ zone. So so along these where the trade winds converge. And that fluctuates, like we talked about last time. It fluctuates because of the tilt of the Earth and if we're in summer versus winter. But if we look at El Nino, though, this is normal. So normal, we have this surface water is being pushed because of the trade winds. And this is warm water because we've got the equator here. And then remember, this water is being displaced and it needs to be filled in. So that's the upwelling. So on an El Nino year, what happens is the trade winds either slow, stop, or even reverse if it's a really bad El Nino year. And we really don't understand why. So we understand what's happening, but we don't understand why it's every 3 to 7 years and why it's kind of this normal oscillation. That's really kind of not very well understood. But you can see here the trade winds have actually reversed direction. And so what happens is this warm water is pooling up along South America. So we don't have upwelling. So notice how upwelling has stopped. Well, what happens here, and I said upwelling brings us nutrient-dense water that's really important for fisheries. So people that rely on fishing are devastated during El Nino years. And so because the fish move on. So the fish, the open ocean, they can move around. So the fish go elsewhere to get the nutrient-dense water and the krill or whatever they're eating. So they disappear. And so people like the fisheries off of Peru and South America really are affected tremendously because people can't just go all over the place, especially if they've got small fishing vessels. So anyways, and then it just creates this big kind of weather patterns too. So it's not just the ocean currents, but remember the ocean currents drive weather. And so if the ocean currents are changing, for that year, that El Nino year, then weather patterns change too. So for example, in an El Nino year, we tend to have in Redding, we tend to have really wet winters during El Nino years. And that's our weather patterns change all along the west coast of North America and South America. And this primarily happens in the Pacific Ocean. So because we have a large, the Pacific Ocean is very large, and we have these really steady trade winds that blow across a vast amount of space. So we see a little bit of this, kind of a very small, not really devastating impact in the Atlantic. It's mostly just the Pacific. But you can see it definitely changes things. And it's only for the year, and then things kind of just balance out. And it goes back to being a normal year. So not only does it affect fisheries, but it also affects weather patterns. So some places that are super wet may be dry. Some places that are super dry may be soaked. And that's kind of how it changes for the year. So, and then kind of the opposite is La Nina, which we'll talk about later. But El Nino is the big one. And in El Nino, every 3 to 7 years, just know that that it creates this upwelling stops. And then it creates this kind of fishing disturbance, and then weather disturbance too. That's the most important things to know about El Nino. All right, and that's it. We'll talk about biomes next time. See you guys later.